Gravity is not what we were taught it is. What we were taught as a force is in reality a mathematical map, one that describes how matter and time move through curved space-time. This map works so well that we rely on it to guide satellites, predict black holes, and synchronize the clocks that run modern civilization. But here is the problem. When we push this map beyond familiar territory towards singularities, quantum scales, or the dark sector, it stops giving reliable predictions. The equations return, infinities, energy accounting fails, and our standard notions of cause and effect no longer produce consistent results. This is not a story about refining a theory. It is about confronting the possibility that our most trusted description of gravity is only an effective approximation, and that the deeper foundations of reality remain largely unmapped. Close your eyes for a moment. Focus on exactly what your body is feeling right now. You likely feel a heaviness pressing you into your chair, or the solid ground pushing hard against the soles of your feet. Your brain interprets this sensation as weight, a downward pull caused by the Earth. But your sensory system is mislabeling the signal. In reality, there is no force pulling you down. What you interpret as weight is actually a resistance force. At the atomic level, the electromagnetic field of the floor is strongly repelling the atoms in your feet, physically preventing you from following your natural path through the universe. If the floor suddenly vanished, you would instantly enter a state of freefall, your natural, unforced state of motion. This creates a conflict between your biology and actual physics. Your vestibular system, the balance sensors in your ears, tells you that you are stationary. But the geometry of spacetime dictates that you are currently being accelerated upward by the surface of the Earth at 9.8 meters per second squared. You are not at rest. You are in continuous contact with the planet, being forced away from your natural path. If your most fundamental sensation of physical reality is a biological illusion, what else is the universe hiding from you? For over 3 centuries, we navigated the cosmos using Isaac Newton's map. He described gravity as a tether, an invisible force that reached out across the vacuum to bind planets to stars. It was intuitive, it was elegant, and it was fundamentally incorrect. Albert Einstein didn't just refine Newton's map, he replaced its underlying framework. He revealed that space and time are not a static stage, but a dynamic, four-dimensional fabric that curves in the presence of mass. Objects don't orbit because they are pulled. They orbit because they are sliding along the natural curvature of this fabric, the geometric gradient. General relativity is the most successful theory in the history of physics. It is the effective map that allows us to synchronize global communication networks and predict the motions of galaxies with terrifying precision. But we must be intellectually honest. It is still just a map, not the territory itself. And like any map, it has boundaries. It works perfectly in the safe waters of our solar system. But as we are about to see when we push this model to its absolute limits towards the quantum realm and the dark sector, the lines begin to blur. Let's begin the investigation where the map is still reliable, with the evidence that first revealed gravity as a geometric effect. What would happen if the cables of an elevator suddenly failed? Panic aside, physics predicts something extraordinary. As the car begins to plummet toward the basement, the sensation of weight in the legs would instantly vanish. The keys in your pocket would float beside you. If you spilled a cup of coffee, the liquid would hover in a perfect sphere. Inside that sealed box, there would be no local mechanical or biological experiment capable of distinguishing this situation from floating in deep space. This isn't just a mental trick, it is the equivalence principle, the cornerstone of general relativity. It suggests that freefall is the universe's default state of motion. When an object falls, it isn't being acted upon by a force. It is simply following the natural geometry of spacetime, following the path of least resistance. Dedicated space missions have been flown to test this principle directly. The French Space Agency's microscope satellite spent 2 years dropping cylinders of titanium and platinum in a vacuum orbit. If gravity were a force like magnetism, it might pull on these materials differently. But the data confirmed with a precision of 1 part in 10 to the -15 that they fell exactly the same way. This experimental evidence confirms that gravitational motion is independent of an object's composition. It is not pulling on your atoms, it is defining the track they run on. This leads to a disturbing conclusion. If falling is the natural state, then sitting in your chair is the unnatural one. An object at rest on the surface is not in inertial motion. It is being continuously deflected from its natural geodesic by electromagnetic contact forces. So if there is no force, why do things move? Why does the apple strike the ground? As a visualization tool, imagine a marble rolling across a stretched surface. If you place a bowling ball in the center, the fabric curves. The marble doesn't know the bowling ball is there. It simply follows the curvature of the surface, spiraling inward. In the cosmos, this trampoline is the four-dimensional fabric of spacetime, and the dip is what we call a geometric gradient. Massive objects like Earth create a steep gradient in this fabric, a slope in the geometry of reality. When you drop an apple, it isn't being dragged down. It is simply sliding down this invisible geometric hill. It is following a geodesic, the straightest possible line through a curved environment. The illusion of force appears because we are usually prevented from following our geodesic. The surface of the Earth blocks our path. We are effectively like a swimmer trying to stand still in a rushing river. The pressure we feel against our legs is the effective geometric gradient, often visualized as a current of space-time directing motion toward the planet's center. We interpret this geometric pressure as weight. But here is the twist that opens the next file in our investigation. This curvature doesn't just bend space, it bends everything within it, including the rate at which reality flows. If mass can distort the path of an object, it can also dismantle the synchronization of time itself. If time feels like a universal constant, a steady drumbeat that ticks the same for everyone everywhere, consider the blue dot on your smartphone's map. That dot represents one of the most precise large-scale applications of general relativity ever deployed, and its very existence proves that time is malleable. To pinpoint your location, your phone listens to signals from satellites orbiting 20,000 kilometers overhead. But these satellites are operating in a radically different relativistic environment than we are. They are caught in a tug-of-war between two opposing physical laws. First, special relativity dictates that because these satellites are moving at 14,000 kilometers per hour, their internal clocks should tick slower than clocks on the ground, losing about 7 microseconds per day. However, general relativity argues the opposite. Because the satellites are far away from Earth's mass, they reside in a region where spacetime is less curved, where the geometric gradient is shallower. Consequently, time there flows faster, gaining them about 45 microseconds per day. When you do the math, 45 minus 7, you get a net effect of 138 microseconds per day. To a human, 38 microseconds is nothing. But for a navigation system relying on signals traveling at light speed, it is an eternity. If engineers didn't manually program Einstein's equations into the satellites to correct this drift, the entire global positioning system would accumulate positioning errors of roughly 10 kilometers every single day. Within a single day, location errors would grow large enough to render the system unusable. The system works only because we accept a strange truth. Time flows at a different rate in space than it does on the ground. If gravity can warp time for a satellite, the next question is disturbing. Does it do the same thing inside your living room? The answer is yes. In a strictly physical sense, your head is aging slightly faster than your feet. In the early 2010s, physicists at NIST demonstrated this effect at the tabletop scale using optical atomic clocks, the most precise timekeepers ever built. By placing two clocks only a few tens of centimeters apart vertically, they detected a measurable difference in the flow of time. The clock on the higher shelf, sitting slightly further up the geometric slope of Earth's gravity, ticked faster than the clock below it. This shatters the concept of global time. There is no single now that applies to the entire universe. As a useful analogy, time behaves like atmospheric pressure. The deeper you go into a gravity well, the denser and slower time becomes. This effect accumulates because the Earth's core is deep within the planet's gravitational well. Theoretical models suggest that over geological timescales, the Earth's core would age measurably slower than the surface, simply because time has flowed more slowly down there over the last 4.5 billion years. We have proven that mass curves space. We have proven that mass distorts time. These are the rules of the map, and in our weak gravity, they are gentle rules. But what happens when we travel to a place where the curvature doesn't just bend, but snaps? What happens when the time pressure becomes infinite? Here, geometry is no longer just an environment, it becomes a lethal constraint. As we move from the gentle slopes of Earth to the precipice of a black hole, the rules of survival change. The danger here isn't crushing pressure as intuition might suggest. It is differential spacetime curvature, what physics formalizes as tidal forces. In physics, this is known as the tidal force. It arises because the gravitational pull at your feet is stronger than the pull at your head. On Earth, this difference is microscopic, far below anything a biological system could ever detect. But as you approach a stellar mass black hole, a collapsed star perhaps 10 times the mass of the Sun, the gradient steepens exponentially. Long before you reach the event horizon, the difference in curvature between your feet and your head reaches levels that exceed the structural limits of biological tissue. Your body is subjected to extreme vertical traction. This is not a biological sensation, it is a mechanical failure. First, your joints dislocate, then muscles tear. Finally, the tensile strength of your connective tissue is exceeded. The tidal geometry overwhelms the electromagnetic forces that normally hold biological structures together. You are snapped, stretched, and drawn out into a stream of subatomic particles. Physicists call this spaghettification. It is a clinical term for the total dissolution of biological structure by geometry. Paradoxically, the situation is different near a supermassive black hole like the one at the center of our galaxy. Because the event horizon spans millions of kilometers, the geometric slope at the boundary is surprisingly gentle. You could cross the event horizon without feeling any pain at all. You would check your vitals and find them normal. You would look back and see the universe still shining. But from the perspective of the outside universe, you are already causally lost. You have crossed a causal boundary from which no future path leads outward. In this region, space-time itself is being carried inward so rapidly that all future directed paths point toward the center. You are not being pulled. You are sliding down a collapsing riverbed where tomorrow is no longer a time but a place, the center. We call the center of a black hole the singularity. But we must be careful with our language. The singularity is likely not a physical object, a dark rock, or a dense ball of matter. In our current framework, the singularity appears as a mathematical error message. When we feed the coordinates of a black hole's center into Einstein's field equations, the math breaks down. It predicts that density becomes infinite. It predicts that space-time curvature becomes infinite. In mathematical terms, this is analogous to a division by zero. It doesn't mean a very large number. It means the theory has stopped making sense. It is the point where the map ends, but the territory continues. We know these objects exist. The Event Horizon Telescope has captured the silhouettes of the black hole in galaxy M87 and the supermassive black hole at the center of the Milky Way, confirming that Einstein's predictions hold true right up to the very edge of the abyss. But at the center, general relativity clashes violently with quantum mechanics. One theory says the point is infinitely small. The other says you cannot pinpoint a particle to an infinitely small location, as dictated by the uncertainty principle. This conflict creates the information paradox. If information falls into this breakdown, is it deleted? If so, it violates the laws of quantum physics. If it survives, where does it go? We don't know. The singularity represents the ultimate failure of our current effective map. It is a hole in our understanding of reality. We cannot fix the map yet. We cannot resolve the singularity. But as a species confined to biological bodies, we are less concerned with the mathematical apocalypse at the center of a black hole and more concerned with the biological apocalypse of simply leaving Earth. When the map fails us, engineering attempts to compensate for what the map cannot explain. We are creatures designed for the bottom of a gravity well. Every system in the human body, from cardiac circulation to skeletal density, evolved under a constant downward acceleration of 9.8 meters per second squared. When we leave Earth, we enter a hostile environment. Without the mechanical stress of gravity, the body interprets the environment as pathological and begins to downregulate non-essential structures. This follows Wolff's law. Bone remodels itself in response to mechanical loading. In 0G, that load is zero. Astronauts lose 1% to 2% of their bone density every single month. Their fluids shift upward, bloating their faces and confusing their kidneys. And since we cannot pack a planet's worth of mass into a spaceship to create real gravity, engineers are forced to hack the system, not by recreating gravity, but by compensating for its absence. we stop trying to recreate the cause-curve spacetime itself and focus entirely on simulating the effect through acceleration. The most elegant solution is linear acceleration. Imagine a spaceship built like a skyscraper with the engine at the bottom. If that engine accelerates continuously at one go, the floor pushes up against your feet exactly as hard as Earth does. It relies on the equivalence principle. Your body cannot tell the difference between standing on a planet and being pushed by a rocket. But this approach requires sustained energy expenditure on a scale far beyond any realistic propulsion technology. If we cannot curve space and we cannot accelerate forever, we must curve our own path. This leads us to the concept of spin gravity. By spinning a spacecraft, we use inertia to pin the crew against the outer hull. This is not gravity, it is inertia redirected by a rotating frame with the floor intercepting your body's natural trajectory. It is a centrifugal patch for our biological limitations. But this patch comes with a sickening price, the Coriolis effect. On a small rotating station, the gravity at your feet would be significantly stronger than at your head. Worse, if you turned your head quickly, the fluid in your inner ear would move in a different geometric arc than the station, often causing severe disorientation and motion sickness. To make this illusion convincing enough to fool the human body long-term, we need size. Calculations for structures like the O'Neill cylinder suggest we need rotating habitats on the scale of hundreds of meters, vast, resource-intensive engineering structures, just to replicate the sensation of standing still. We are building prosthetic environments to survive in a universe that is indifferent to our biology. But even if we successfully engineer our own local gravity, we are still adrift in a cosmos that is largely invisible to us. We can fix the environment inside the ship, but outside the map of the universe is missing the variables that matter most. The universe is expanding faster than our current models predict. In 1998, astronomers measuring the light from distant supernovae expected to see the expansion of the universe slowing down, dragged back by the collective gravity of all the stars and galaxies. Instead, they found the opposite. The cosmos is accelerating. Galaxies are being pushed apart by an invisible driver whose influence becomes dominant as space expands. To reconcile general relativity with these observations, physicists introduced a new variable into Einstein's equations called lambda, also known as dark energy. This is not the discovery of a directly observed substance. It is a mathematical placeholder. We call it dark energy, which drives cosmic expansion, and dark matter, which holds galaxies together. But these are ultimately just labels for our ignorance. In the current standard model of cosmology, the lambda CDM model dark energy makes up roughly 68% of the universe. Dark matter comprises another 27%. The normal matter, the atoms that make up stars, planets, and your body, accounts for less than 5%. We are not the main characters of this reality. We occupy only a negligible fraction of a vast, largely invisible cosmos. Missions like the Euclid Space Telescope are currently mapping the geometry of this dark sector, trying to determine if lambda is truly a constant energy of space, or if gravity itself behaves differently on cosmic scales. But the deeper we look, the more the map begins to tear. The crisis reaches its peak when we try to explain why the universe is pushing itself apart. We have two best maps of reality: general relativity for the large-scale structure of the universe, and quantum mechanics for the microscopic world. Both work perfectly in their own domains. But when we use quantum field theory to calculate how much energy should exist in empty space, the so-called vacuum energy, it produces a prediction. When we look at the actual expansion of the universe to measure that energy, we get a different number. They do not match. In fact, they disagree by 120 orders of magnitude, a difference of 10 to the power of 120. This is known as the vacuum catastrophe. It is widely considered the worst theoretical prediction in the history of physics. It's not just a rounding error. It's as if one map says the distance to the moon is measured in centimeters, while the other places it billions of light years away. This discrepancy is the smoking gun evidence that our understanding of gravity is fundamentally incomplete. The problem isn't that we haven't explored enough of the universe. The problem is that we are viewing it through a theory that is now in direct conflict with the laws of quantum physics. We are trying to navigate a quantum ocean using a classical map. When two maps of the same territory contradict each other by 120 zeros, It is a sign that the underlying structure of reality is far stranger than either map can currently describe. So finally, what is gravity? It is the geometry of the space-time structure we inhabit. It is the rule that says matter tells space how to curve, and space tells matter how to move. It is the reason your feet are pressed to the floor, the reason your GPS works, and the reason time itself is not a single global arrow, but a locally defined flow. We have successfully traded Newton's invisible tether for Einstein's dynamic fabric, and that trade has given us the keys to the cosmos. But as we close this file, we must accept the verdict of our investigation. The map is not the territory. General Relativity is a masterpiece, but the existence of singularities and the vacuum catastrophe proves that it is an approximation. It is a low-resolution image of a much deeper, high-resolution reality. Just as Newton's laws worked for cannonballs but failed for Mercury's orbit, Einstein's equations successfully describe black holes down to their horizons but break down when pushed toward the quantum vacuum. Physicists are now searching for the next layer of the map. Perhaps spacetime itself is not fundamental but composed of discrete pixels or loops at the Planck scale. Perhaps gravity is an emergent property like heat arising from the motion of atoms. We are waiting for a new framework that can see beneath the geometry itself. Until then, remember this. When you drop a cup and watch it shatter, you are witnessing the interaction of the most profound forces in existence. You are watching an object follow a geodesic through curved four-dimensional space, intercepted by the electromagnetic resistance of the floor in a universe that is expanding faster than our current theories can explain. The sensation of weight is a reminder that you are part of this structure. We are all embedded in this geometry even here in an ordinary chair. The map may be incomplete, but the ride is real.